There are a million ways to cut metal. The speeds, feeds, techniques, tolerances, and materials, there's so many options, it feels like when you finally settled on an approach, two more pop up. Well, I'm here to tell you about a technique that typically flies under the radar, but from what I've seen, leads to massively increased productivity, reduced downtime, and overall more jobs coming through your shop. That technique is called high feed milling. If you've never tried high feed milling or heard that it's some complicated, not so worth it method, or maybe you even have a buddy who tried it and broke some tooling, well, I'm here to tell you it does have some quirks, but once you learn them, it's actually really easy to apply. Today, we're going to hear from Eddie, Horn Academy manager here at Horn USA, to learn the what, how, and why of high feed milling so that we can figure out how to apply it for your next job. Let's go check it out. All right, so to get started, tell me a little bit about high feed milling and what it is and some of the basics.
Well, high feed milling is the use of higher feed rates, typically maybe 6 times a normal feed rate, in order to rough mill a component. So the basics of high feed are you're looking at parts with long stick out, so where your arbor extends a long distance from the spindle nose. You're also looking at maybe difficult materials like titaniums or stainless, where it becomes imperative that you have the max stability. So the main concept of high feed is that you're putting the force into the spindle instead of radial force. You can run high feed cutters on 40 taper machines, BT30 machines, on up to your HSK 100 machines. It's how that spindle reacts to the forces in cutting is going to be important, and whether that cutting is more economical than using a 90-degree tool and using multiple step downs to remove the volume. The big catch though is depth of cut. So typically your depth of cut is anywhere from 20 to 60 thousandths. Can be more depending on the size of system. You're going to stay under that maximum depth, but you're going to do that at 6 times the feed rate. So in a situation where you would have a long stick out, let's say a 90-degree mill, you would have to reduce your cutting section in order to maintain a stable cut. With high feed, you're able to cut at high feed rates. It comes down to basically comparing the cutting volume that you can do with high feed versus what the cutting volume of an A style or any other technology like 45-degree mill you could achieve.
And I've also noticed on high feed inserts that the cutting edge has a radius on it. Could you tell me more about how that radius is determined and then what that leads to in the finished part?
You can think of high feed like a giant round insert. So we know round inserts, because of that median chip thickness effect, can take, at low depths, can take higher feed rates. So it's the same concept. So on a high feed tool, the end radii the form might be a large 22.5 millimeter radius. So it's effectively taking that radius and just using the part of it you need to make the cutting, rather than have a full part of the insert. So chip thinning takes advantage of the geometry of the cutter and the forces and gives you that ability to take higher feed rates. At the end of the day, your chip thickness the average is going to be much less than a 90-degree cutter. The tool is tipped anywhere from 16 to 20 approximation of a kappa R lead angle. So it's not going to make a flat all the way across the part. It's going to make a kind of a dip. So you have to account for that in your step over. Your feed can go higher and your average chip thickness still stays pretty good.
Okay.
So that gives you that advantage, because we know if you take a 90-degree cutter for a specific material system, there's only a certain maximum section you can take in one rotation.
And what would be some of the disadvantages that maybe a conventional A style or a 45-degree cutter would be better than high feed?
A styles would probably be better if you don't have a very well-maintained machine. If your spindle pull force is diminished from the compression washers not being very, very good, or you have old retention knobs, or things are just not very stable. While most of the force is pushing into the spindle, you do have some axial force. So if you have extremely thin walls, you can push the material around.
I've heard that high feed can't make sharp corners. Is that correct?
Yeah, there's a couple of things you want to be careful of with high feed. First, don't change acceleration. So if you're going into corners, you need to be driving radii. You don't want to change directions abruptly. You are creating more force in the axial direction rather than radial, but you run the risk of the tool springing back and sort of damaging the insert. The other programming consideration is always be careful about your depths. So if you're helical boring into a part, make sure you start above the part. Never assume that your rough material is exactly as it was specified. Exceeding the depth is really bad on high feed tools. It causes a lot of damage to the cutting edge and possibly tool failure. So always, number one rule of high feed, respect the depth of cut at all times.
Are there any other industries or applications that high feed is typically used for?
Really across all industries, anywhere where you need to remove a lot of material. If you're removing a small amount of material, maybe it's not the most economical way to do it.
Sure.
But if you're removing a lot of material and roughing, that's high feed is a good choice. It is the best at long reach applications. So the further you stick your tool out from the spindle, we know our parameters have to go down. You can't stay at a normal sort of book parameter 8 times from the spindle. So with high feed, you can achieve that and still maintain a stable process, a safe process where your inserts aren't destroyed every component, and you have long, stable, low risk runtime.
As a consideration between indexable and solid carbide, what are some of the things that you should pay attention to when making that choice?
Solid carbide is a good choice for small parts, so for very small parts, but indexable is usually the best solution. Cost of the tool is much less. You're not going to have to pay for a lot of carbide that you're not using. So indexable is really a best solution for larger roughing, but in general, indexables are a good solution for heavy roughing and bigger parts. Solid carbide for small parts.
Talking about parameters for high feed, I know speeds and feeds are a little bit different, but also, like we mentioned, depth of cut and step over are different than conventional tools. So how do you go about setting that up?
Step over, you just need to keep in mind that the actual cutting edge is at that angle. So the flat sort of area that it's going to cut is going to be less than a 90-degree tool. So a 90-degree tool is going to go, if it's a 2-inch diameter cutter, it's going to cut a 2-inch wide swath minus the corner rads on the insert. High feed, you're going to have to look at the manufacturer's recommendation or their specification to see just what the step over needs to be to make a flat surface. Okay. Now, if you're just roughing and you don't care about that, you can use the full tool, but you're going to have cusp on that Z-level surface. 60 degrees is kind of the sweet spot for most milling. Cutting speed is going to be similar. For the most part, you can use speeds that you would use for a 90-degree cutter. Now, the advantage that you can have with high feed is that the depth of cut notching is much less pronounced on a high feed tool because there's very low area for oxygen between the cut. So you have reduced depth of cut notching compared to a 90-degree tool. On the feed rates, best way to determine the feed rate, look at the manufacturer's suggested. I would always recommend, do testing. Start on the low end of the depth or kind of mid-range of the depth, low end of the feed, and then do some tests. Ultimately, you're going to want to see where your machine system is happy, and that's going to change according to how much you have it stuck out from the spindle. So the longer you stick it out, the more you have to adjust those parameters. But it should always result in purchasing the tool, understanding all the cutting conditions, and then do internal testing to see where the limits are. Only change one parameter at a time and then you can adjust incrementally 10%. Once you're comfortable with the feed, then you can back that down and say, okay, my max feed and my max depth are this for this particular system. It's a little bit labor intensive process, but it's worth it because you won't end up running a tool and saying, oh, this doesn't work.
Now that you have your parameters dialed in, that's when you can calculate MRR and see the efficiencies gained over conventional milling?
You can just use a calculation cost per cubic inch. That will factor in the machine value per hour, operator value per hour, how long it takes you to change the inserts, and then the cubic inches of removal or cubic centimeters or removal comparison. So that's the best way to sort of compare dissimilar technology and get the right choice.
Now that we've covered the basics of high feed milling, I understand that you've prepared a demo for us to see some of these principles in action, so let's go check it out.
Sounds good.
All right, it looks like we're watching a clip of the DAH37 cutter in 316 stainless, and to me it looks like the feed rate is really high and there's no chip control problems, and it's removing quite a bit of material.
Yeah, and the other point to notice is the finish. So a lot of people get sort of disappointed in high feed about the finish that it leaves, but at the end of the day it is a roughing cutter. You want to just remove a material, get it off of the part. So you can see from this part the finish that typical you would get in a high feed tool. Now this sample is a piece of 42 chromium moly, which is 4140 in SAE standard. But you can see this is at feed 1 millimeter, 40 thousandths per tooth, and a cutting speed of 250 meters. So typical parameters for speed, but very aggressive feed parameters. Okay. Where this makes a difference in a piece of stainless or a piece of titanium or whatever the case is, difficult materials, you're actually getting an advantage, a lot bigger advantage with your feed parameter. Let's say titanium for an A style might be 4 thousandths per tooth. Well, if I can take more per tooth in a titanium, I'm going to be a lot more productive. Same with stainless.
Gotcha. And kind of going back to the pattern that high feed leaves, I noticed that here in the center, this is pretty much perfectly flat, but on the edges, it has that curved shape. And when you run that multiple times, it leaves a little bit of a scallop. There is some deviation, but not enough to harm the next tool that would come back to finish it. Is that correct?
Yeah, you're going to change your step over to accommodate a more flat surface because of the shape of the tool. And these cusps aren't going to harm the next tool whatsoever when you're semi-finishing or finishing.
And of course, that's 316 stainless. We also did it in 4140 and then 6061. Are there any considerations that you might want to make when working with different materials, either harder, softer, more difficult to cut?
With very sticky materials, coolant is always advisable. If you're on a 4140 or normal steel, you can get away with dry machining with high feed. That's going to depend a lot on the situation. Mainly with high feed tools and steels, the coolant is really just to remove the chips from the pocket because you don't want to recut. It's just like any cutting tool, you don't want to recut chips.
Now we can see the DAH37 in 4140, and to me it looks a little bit faster. Is that true because you're working with a different material compared to the 316?
So the RPM is controlled by your cutting speed. So 316 is going to have a lower cutting speed than a 4140. The cutting speed is the main driving determinant of what that productivity is in the case of changing different materials. A piece of titanium might run 160 surface feet or 50 meters per minute cutting speed, but still can benefit from productivity of high feed milling. So you want the largest diameter cutter with the most number of inserts because we know it's RPM times feed per tooth times number of teeth. So you get higher feed rate and more productivity. But you also have to balance that with what are my horsepower limitations, what is the rigidity limitation of the machine. Obviously, the bigger the cutter diameter, the more force you're inducing into the system. And some machines, you have to go lighter on depth of cut, lighter on feed rate to make that productive.
And then when you get to larger cutter diameters, whether solid carbide or indexable, are there benefits that you can take deeper depth of cuts because the insert size increases?
Different sizes of high feeds are available. We have a DAH37, we have the DAH82, we also have a DAH84. So as the size of the insert goes up, the depth of cut capability goes up. There is a diminishing return though, once you get to a certain size IC, like say a 16 millimeter IC insert, then you can start running into trouble with the machine not having enough rigidity, enough horsepower to drive that cutter. And also the number of inserts you can fit on a given diameter goes down. It's all about balancing all the features and parameters together to make sure that you're getting the best out of the high feed cutter.
And comparing between the DAH37 and the DAH84, or the 82 even, it looks like this one, the 37, has 3 cutting edges, and this one, the 82, has 8, and is a double-sided insert. Can you tell me about the benefits and drawbacks of each of those?
The 37 is what we would call a single-sided insert. So it has 3 usable cutting edges. It has more of a primary rake. That's going to have, usually you'll have a higher ramp angle. So with double-sided inserts, the ramp angle is always less. So if I'm pocketing and I have limited space for ramping, I might choose a DAH37. If I have just open pockets and I can helical in and take step levels with the tool, then the 82 might make more sense.
And then looking at the other tools here on the table, we have a 45-degree cutter, the M409, and then a more conventional end mill, the DPSV. Talk me through some of the comparisons between these different tool systems.
So for a high feed versus the 409, so that's a 45-degree cutter. So with a 45-degree cutter, I'm going to do mainly face milling. In some respects, the high feed will do what the 409 will do, but it also has the capability to go in a pocket and produce a fairly straight, rough wall for a finishing tool. So what you would do is kind of a 1, 2, 3 punch the DAH82 to rough the pocket, the 45 maybe to clean the floor or parts that need to be very flat, and then the end mill to do the finishing on the wall. Unfortunately, there's no universal tool that exists out there that will do everything, so it's about planning your process, looking at the productivity in real numbers, calculating what the cost per cubic inch is, and then making a decision based on that and on testing at the machine.
All right, Eddie. Well, thank you for your time and answering my questions about these tools. If there's 3 takeaways that we should learn from this video, what would they be?
Well, let me start with high feed. High feed, number 1, depth of cut. Number 2, depth of cut. Number 3, depth of cut. The top 3 things, really honestly, just look at your manufacturer's recommendations and follow those. Make your own internal testing, go step by step, 10% increments, change 1 parameter at a time. And third, pick the biggest tool that has the most flutes that makes economical sense for your application. So always do a calculation, figure out what the cost per cubic inch would be, and then work from there.
All right, guys, I hope you enjoyed that short overview of high feed milling. If you'd like to learn more or try the tools for yourself, please reach out to one of our local Horn sales reps using the contact information below. We at Horn USA are here to support you, the American manufacturers, with the techniques and tools that you need to remain competitive and stay successful. If you enjoyed this video or got something out of it, please be sure to leave a like and subscribe so you don't miss future content. I hope to see you in the next one. Thanks.
What's up guys, I'm normally behind the camera, but if you made it this far in the video, I want to thank you for watching. Why not leave a like? Go ahead and subscribe to the channel while you're at it too, and click the bell for notifications to be notified when we drop a new video. We upload new videos to this channel every week about education, product trainings, collaborations, promotions, whatever we got going on here, and there's quite a bit. Also, if you're on LinkedIn, we're active over there too, so go over there and give us a follow. We also have a new redesigned eShop on our website where you can go and easily find and order tools straight from us. And also check out Greenline. Greenline is a new service that we offer in the United States that can get your tools from design to out our door in less than 5 days. So, I don't know about you, but custom tools in less than 5 days sounds like a pretty sick deal. That and so much more is happening right here at Horn USA in Franklin, Tennessee. Thanks again, I'll see you next time.